We have gone through the orthogonality property of Legendre's polynomial in previous lecture. Today we will use that orthogonality property in solving some of the numerical problems based on Legendre polynomials. So let us see, I have selected the first problem in which we have to evaluate this integral, which is integral from minus 1 to plus 1 x square minus 1 pn plus 1 times pn dashed dx, and that is equal to 2n into n plus 1 over 2n plus 1 into 2n plus 3. So let us see how we will solve this integral by the use of orthogonality property of Legendre's polynomials. First of all, we will start with the fifth and sixth recurrence formula, and you will see starting with these recurrence formula we will obtain a particular result which is known as Beltrami's result, and after that you will be able to evaluate this integral. So let us see, your first recurrence relation is what? This is 1 minus x square pn dashed equal to n into pn minus 1 x pn. And the sixth recurrence relation you have studied, this is 1 minus x square pn dashed equal to n plus 1 times x pn minus pn plus 1. So these are the fifth and sixth recurrence formula or recurrence relation you can see. Now let us multiply this equation A by n plus 1 and the another relation defined in equation B by n. First of all, we will multiply the equation A by n plus 1 and then B by n, and after that we will add these two. So you can see the sum will be this much: n plus 1 into x into 1 minus x square pn dashed plus n into 1 minus x square pn dashed, and that will be equal to n into n plus 1 times pn minus 1 minus x pn plus x pn minus pn plus 1. So you can see this minus x pn and plus x pn will cancel out, and so our result is this. And in this LHS, let us take this 1 minus x square pn dashed as a common factor. So in first term there will be n plus 1, and in second term only n remain left. So this is n plus 1 plus n into 1 minus x square pn dashed, and that is equal to, you can see here, n into n plus 1 into pn minus 1 minus pn plus 1. Now this n plus n, that will be 2n, so this is 2n plus 1 into this much, and that equal to, the RHS remains at is actually n into n plus 1 into pn plus 1 minus pn minus 1. So this result which we have obtained in this equation 1 by the use of the fifth and sixth recurrence formula, actually this result is known as Beltrami's result. Now using this Beltrami's result we will be able to evaluate the given integral, and for this you can see from this equation 1, from equation 1 you can see what will be the value of x square minus 1 times pn prime. What will be this? This is simply n into n plus 1 over 2n plus 1 into p n plus 1 minus p n minus 1, and let us say this is equation 2. Now to evaluate that integral, you can see the integral first. We have to evaluate integral from -1 to +1 x square minus 1 into Pn plus 1 into Pn dashed. So, to evaluate that integral, we will simply multiply this equation 2, both sides, by the factor Pn plus 1. And then we will integrate this equation with respect to x from -1 to +1. So you can see multiplying both sides. Multiplying both sides of equation 2 by Pn plus 1 and then integrating with respect to x from -1 to 1, or you can say +1. We have. What will be our result after that? You can see. You can see this will be simply minus integral -1 to +1 x square minus 1 into here is Pn dashed and we have to multiply by Pn plus 1. So this will be Pn plus 1 into Pn dashed dx, and this will be equal to, in RHS you can see here there is n into n plus 1 over 2n plus 1. This is a constant factor, so we can take it outside of the integral, and in the term inside the bracket we will simply multiply by Pn plus 1 in both terms. So this will be equal to n into n plus 1 divided by 2n plus 1 integral from -1 to 1 and Pn plus 1 times Pn plus 1 minus Pn minus 1 dx. Now we have to evaluate actually this much. So let us simplify the RHS of this equation. So this will be n into n plus 1 over 2n plus 1 and integral -1 to 1 Pn plus 1 square dx and minus integral -1 to 1 Pn plus 1 into Pn minus 1 dx. Now we have already studied, let us say this is equation 3, the orthogonality property of Legendre's polynomial, and you know what are those orthogonal properties. So from orthogonality of Pn of x, we have already studied this in previous lecture, and you have seen that this property says integral -1 to 1 Pm of x times Pn of x dx, and that is equal to 0 if m is not equal to n, and this is equal to 2, this is 2 over 2n plus 1 if m is equal to n. Say this is equation 4. We have already studied this property of Legendre polynomial in the previous lecture. So now let us use this orthogonality property of Legendre's polynomial in this equation 3. You can see in this problem, actually here m, you can say, is equal to, if m is equal to n minus 1, then n is equal to n plus 1. So in the first term, you can see that there is Pn plus 1 square. It means here m is equal to n. And in second term, there is Pn plus 1 into Pn minus 1. So in second term, in fact, m is not equal to n. So here, when we will use the orthogonality property of Legendre polynomial, then simply this second integral will actually vanish. And so you can write, so using 4 in 3, we have what you will get. You can say the integral in LHS is integral from minus 1 to 1 x square minus 1 Pn plus 1 Pn prime dx, and this will be equal to n into n plus 1 over 2n plus 1. And as you can see, in accordance with equation 4, the first integral will be non-zero, that will be found by using this result, and the second integral will be 0. So what will be the first result? This will be 2 over 2n. Here n is in fact n plus 1. This is n plus 1. Plus 1, so here will be 1, and minus 0. So you can see this is simply 2n into n plus 1 over 2n plus 1 into 2n plus 3. And this is the result which we have to prove. So you have seen how easily we can solve such problems if you remember the recurrence formula and the orthogonality of Legendre polynomial. So now let us see the solution of the second problem. I have selected this second problem in this way. This is integral from minus 1 to plus 1 x square Pn plus 1 times Pn minus 1 dx, and that is equal to this much. So first of all, I am again rewriting this problem, and then we will solve it. So first of all, I am going to write the second problem. So you can see the second problem is to prove, we have to prove actually integral minus 1 to plus 1 x square Pn plus 1 into Pn minus 1 dx, and that is equal to 2n into n plus 1 over 2n minus 1 into 2n plus 1 into 2n plus 3. So this is the result which we have to prove here. So again, for the solution of this problem, we will start with an appropriate recurrence formula. In fact, you can solve this problem starting with the recurrence formula number 1, which we have discussed in the previous lectures. So from the recurrence relation 1, you have seen what is that recurrence relation. Actually, I am writing that recurrence relation in another page. See here, this recurrence relation is 2n minus 1 into x into pn minus 1, and this is equal to n pn plus n minus 1 into pn minus 2. This is actually the first recurrence relation which you have studied in the previous lecture. Now, in this recurrence relation, we will simply replace this n by n plus 2. So you can say replacing let us say this is equation 1, and now replacing n by n plus 2 in this equation 1 we have. When you will replace n by n plus 1, this n by n plus 1 in this equation 1, what will be your result? You can see here is 2n minus 1. So now n will be replaced by n plus 2. So this will be 2 into n plus 2 minus 1 into x pn minus 1. But n will be now replaced by n plus 2. So this will be n plus 2 minus 1, and that equal to n. N is now n plus 2, you can see. And pn, now n will be replaced by n plus 2 and plus n minus 1. So now n will be written as n plus 2 and minus 1, and here pn plus 2 minus 2. So let us see what this recurrence formula becomes. Here will be 2n plus 3. This is 2n plus 3, because this will be 2n plus 4 minus 1, and 4 minus 1 will be 3. So this is simply 2n plus 3 into x p. You can see 2 minus 1 will be plus 1. So this will be pn plus 1. And that is equal to n plus 2 into pn plus 2. And in last term, since here is 2 minus 1, so that will be plus 1. So this is plus n plus 1 into, and here 2 and 2 will cancel, so this is simply pn. And let us say this is equation 2. So I have actually modified the first recurrence formula by substituting n plus 2 at the place of n. Now, to get the value of this integral, you can see I have to evaluate the integral x square pn plus 1 into pn minus 1 dx. And in our result, there is pn plus 1. So we will now simply multiply the corresponding sides of this equation 1 and this equation 2. And after that, we will integrate the result with respect to x between -1 and +1. So now let us first of all multiply the corresponding sides of these two equations. So multiplying the corresponding sides of equations 1 and 2, we get what will be our result after this multiplication. You can see easily in LHS in equation 1 the term is 2n minus 1 into x pn minus 1 px 2n minus 1 into x pn minus 1, and in this equation 2 the term in LHS is 2n plus 3 into x pn plus 1. So you can see this will be after multiplication of this LHS term by this LHS term, what will be our result? You can easily see this will be 2n minus 1 into 2n plus 3 into this x into this x, this will be x square, and this pn minus 1 into pn plus 1, and in RHS you can see we will multiply this term by this term. So what will be our result? You can see here when n pn will be multiplied to this n plus 1 pn. So this will be n into n plus 1 into pn square, and plus when this pn plus 2 and this pn, this pn minus 2 and pn, this will be multiplied, then you will get n into n plus 2 into n into n plus 2 into pn plus 2 into pn. So I have multiplied now this n plus 2 into pn plus 2 with this npn, and plus you can see now this n minus 1 into pn minus 2 will be multiplied by this first term. So what will be that? This is simply n minus 1 into n plus 2 into pn minus 2 into pn plus 2. Now finally we will multiply this n minus 1 into pn minus 2 with this n plus 1 into pn. So this will be n minus 1 into n plus 1 into pn minus 2 into pn. So this is the result obtained after multiplying the corresponding side of equation 1 and equation 2. Now we will simply integrate this result with respect to x between the limits minus 1 and plus 1. So you can see what will be our result. So integrating equation 3 with respect to x between the limits minus 1 and 1. We have what will be our result? You can see easily. This will be simply in LHS there is the factor 2n minus 1 into 2n plus 3, and this is a constant factor, so we will take it outside of the integral, and integral minus 1 to plus 1 x square into Pn minus 1 into Pn plus 1 dx, and this will be equal to what? See the first term. The first term is n into n plus 1, and this is a constant factor, so it will be outside of the integral, and so this is integral from minus 1 to plus n Pn square dx plus. Now see the second term in RHS. This is in fact n into n plus 2, and this is a constant factor, and so this will be outside of the integral, and so this is integral minus 1 to plus 1 Pn plus 2 into Pn dx. Now see the third term in RHS. This is n minus 1 into n plus 2 integral from minus 1 to plus 1 Pn minus 2 into Pn plus 2 dx, and plus the last term. This is n minus 1 into n plus 1 and integral minus 1 to plus 1 Pn minus 2 Pn dx. Now we will use in this equation the orthogonality of Legendre's polynomial, and you know we have just seen what is this orthogonality property from orthogonality of Pn of x. You have seen that integral from minus 1 to plus 1 Pn into Pn dx, this equal to 0. This is equal to 0 when? If m is not equal to n, and this equal to 2 over 2n plus 1 if m is equal to n. So now use this orthogonality property in this equation 4. So you can see here that the first integral in RHS will be non-zero, that will be evaluated by using this formula 2 over 2n plus 1, and all other integrals will vanish, because here you can see if m is n plus 2, then n is n, and so m is not equal to n in the second term. Similarly, in the third term, you can see if m is n minus 2, then n will be n plus 2. So they are different, and so this integral will be also 0. And similarly, in the last term, you can see if m is n minus 2, then n is simply n, and so m is not equal to n. So you can see in this term m is not equal to n. In this term also m is not equal to n, and the last term also m is not equal to n. So all the integrals in which m is not equal to n will vanish. Only the first integral in RHS will remain, and that will be evaluated by using this formula 2 over 2n plus 1. So you can see what will be your result. So our result will be therefore 2n minus 1 into 2n plus 3 integral minus 1 to plus 1 x square pn minus 1 into pn plus 1 dx. This is the integral in LHS, and that will be equal to what? See the first integral in RHS. This is n into n plus 1 into this much. So this will be n into n plus 1, and the value of the second integral you can see from this orthogonality property. This will be simply 2 over 2n plus 1. So we will write here 2 over 2n plus 1. 2 over 2n plus 1. And you have seen in the remaining integral, actually the condition m not equal to n is satisfied. So all those three integrals will be 0. So I am writing the values of those integrals 0 here. And so our result is simply 2n into n plus 1 and divided by 2n plus 1. So you can see now what will be the integral minus 1 to plus 1 x square pn minus 1 pn plus 1 dx. And this will be what? We will simply divide the RHS by this factor. So this will be 2n into n plus 1 over 2n minus 1, this factor here, divide into 2n plus 1 into 2n plus 3. And you can see this is the result which actually we have to prove. So you have seen how easily we can solve these types of problems if we remember the appropriate recurrence formula and this orthogonality of Legendre's polynomials. So I hope you have understand these ideas, and actually such type of problems are very useful in your academic classes and also in different competitive examinations like NET, CSR, and just like those examinations.